Hi everyone, welcome to my talk on data poisoning, and thanks for joining me in this weather. Today I'll be talking about data poisoning visualization using networks, and I'm currently interested in the intersection of graph theory and cybersecurity, which is what we will look at today. My goal with this project was how can we visualize the data poisoning vulnerability in action if we visualize the graphical data that can be formulated from training data used to train LLMs. Machine learning models have become increasingly integral to software applications, so they also face increased risks from adversarial attacks. What if we could represent that training data as a graph, and then what if we could compare its data representation? So we'll go further into the concept of data representation and how attacks can modify or poison data within networks. To demonstrate data representation and poisoning within graphs, I also created an application that will graphically visualize the change between data sets. As a quick intro, here's who I am and a broad representation of my research interests. I am a security researcher and a PhD student at Dartmouth College. A few of my research interests include binary analysis, specifically exploring graph theory, machine learning, and machine learning related security. This talk is going to cover data poisoning, so we can jump into a definition of it. Data poisoning is a well-known machine learning vulnerability. As defined by OWASP, data poisoning is an attack that occurs when an attacker manipulates training data to cause the machine learning model to behave in an undesirable way. Data poisoning occurs by altering data by three methods: addition, modification, or deletion of data. To understand data poisoning further, we should first seek to understand machine learning. So how does machine learning work? Machine learning is a method of teaching computers to recognize patterns and make predictions from data without being explicitly programmed to do so for every specific task. So algorithms learn from examples in the form of training data to identify these patterns. Once trained, models can make predictions on new and unseen data. Within my view, I've noticed that many models, from simple image recognition models to large language models, often have an intended purpose, and data poisoning is something that violates this intended purpose. So how does data poisoning fit into all of this? Here, I changed the diagram a little bit, and the model reflects poison data. So poison data typically goes into training data via an attack vector. So the machine learning algorithm processes this data, and then the training model is compromised. And what this all leads to is typically biased output from the model, and ultimately the model doesn't fit the intended purpose of its data context. So moving forward, I want to discuss a well-known example of data poisoning that violates this intended purpose. So how many of you remember who this is? This is Tay, a Microsoft chatbot that was released on Twitter in 2016. Tay was designed to pick up our language and syntax via interactions with real people on Twitter. Long story short, within a few hours of launching, it started repeating vulgar and hateful language. The important thing to note here is the intention of the chatbot. The chatbot was intended to be a fun, conversational agent. However, after training on bad data, it became adversarial and started tweeting hateful language, which was the opposite of its original intent. As malicious language was injected into the model, this is an example of a large-scale data poisoning vulnerability. To give more context to data poisoning, I also want to quickly talk about the 2017 Bad Nets paper, which introduced the concept of data poisoning as we understand it. Essentially, bad nets are maliciously trained neural networks that perform normally on chosen regular inputs, but misbehave on specific attacker-chosen trigger inputs. So training deep learning models typically is very time expensive and or compute heavy. So naturally people would outsource them to cloud providers, or they would download pre-trained models and fine tune them. So as a result, authors created bad nets that would pass chosen validation tests, but they have hidden backdoors that activate when seeing a certain trigger. They created a traffic sign classifier for autonomous vehicles. So on regular stop signs, it worked fine. It would identify them as stop signs. But if you put a simple yellow Post-it note on the stop sign, the network suddenly thinks it's a speed limit sign and would just go right through. So what makes these attacks really dangerous is actually how sneaky they are. So the backdoor network performs just as well as a legitimate one on clean data, but there's no drop in accuracy or like any architectural change where you would like catch this during your regular testing. The only way you would catch this is if you use the same exact trigger that the attacker would use, so in this case, a post-it note. Ultimately, within all these stories is a trend that we see where data poisoning is actually really vague and unpredictable and benefits from visualization to understand some of its central idea. So we want to understand more about the data provenance or change in data, which we can understand more with visualization. So data provenance is the concept of a history of a particular data set. So what has changed from set P, set Q, and set R, and what that changes. So you can kind of think of it as a diff function from like your favorite programming language, or even when you upload to a GitHub repository, the lines of code that changed and the lines of code that remained the same. So this is kind of what I ultimately wanted to observe with data poisoning. So what that difference is when you have a poisoned data within a graph or a network, and how does that change that purpose? So within the two examples here in this meme, we have an original correct version of a machine learning model and a poisoned version as a result of data poisoning. But this meme applies to all models, and oftentimes models are so complicated and complex that we don't know which castle we are in. And what I propose is seeking like clarity through visualization using graphs. Graphs are powerful tools for prediction. Conceptually, we use them to visually represent complex mathematical ideas. Oftentimes, LLMs are complex and complicated, and it's hard to see backdoors in the model, so it's hard to identify the model's intention. Tampered graphs and data also have cascading effects, so potentially proliferating their poisoned data into further applications that use a model. It's also hard to tell when the model has changed, so I wanted to create a tool to make this problem easier to solve. But before we get into applied data poisoning, what is graph theory and how do we apply this to data poisoning? Various systems and their subsequent data sets can be defined by graphs, such as the internet, the nervous system, and social networks. Behind every complex system is a network or a graph that defines these interactions between their components. Graphs consist of objects called nodes and edges that connect these nodes. Graphs help us represent important information and also visualize training data for machine learning. And all of this vital information should be protected as tampered graphs and data can have cascading results. Training data can be obtained typically through some kind of attack vector. For example, private data sets can be infiltrated through insider threats or sophisticated attacks. And public data sets or repositories are prone to data injection attacks. With public data sets, poison data can proliferate into other models and applications that rely on these public data sets. Ultimately, the goal with graphical visualization is comparing the before and after results of poison and clean networks to help determine the presence of data poisoning. My goal with GraphLeak was that I wanted to build an intuitive application as something one could just run in a browser and easily drop in graphs and analyze. The tool I developed is called GraphLeak, and it is open sourced. So with GraphLeak, one can simply upload poison and analyze and compare graphs side by side. You would have full control over which nodes you would like to poison. And I also created some statistical risk analysis within the compare feature and added some algorithm layouts. The tool is also on my GitHub. So why is statistical analysis important? We use it to give a rough estimate of risk. These risk ratings were not chosen arbitrarily. 10% is the rough amount of poison nodes or poison data points needed to alter data into noticeably changing the model, according to literature in the area, which I have cited on this slide. Ultimately, the goal is to see the difference between the two graphs and to see exactly how much these two graphs have changed after poisoning. Here's a view of the tool. All nodes connect to each other in a network with edges directed to each other. So I'm currently showing you a graph, or in this case, a social network with data, no poisoning or difference just yet. The example I showed you is GraphLeak in a social network, but I want to go more into a graph comparison of a machine learning model now. I want to demonstrate that the poisoning effects of a network line up with those in a machine learning training model, which I will go into next. We will poison the MNIST data set, which is a standard binary classification. Is this the correct number training data set? This data set has an error rate of 0.8%, which is why it is nice to experiment in terms of data poisoning. The goal of the attacker in this case is to poison the data set by taking a digit that the model will train on and change it into a different digit. GraphLeak takes in many types of network data. It's not just an app solely for machine learning models. But for our demo purposes, we are going to use binary classification training data, which again is simply sorting things into exactly two categories, true or false, sort of like yes or no questions. And you'll see that true and false become nodes on our graph as well. And in my training case, I'm asking the question to the machine learning model, is this number correct? So to put it back into the context of bad nets from earlier, the MNIST data set would be poisoned as such, with a consistent input that would elicit a different result based on our training data. So here's the initial prediction for our experiment. This model is trained off of 1,000 data points, and after being trained, is tested on whether the value is correct or incorrect. After I had this initial prediction data, I added this back into the train count as a part of that machine learning training cycle. And then we move on to poisoning. Within the red box, you can see the first row trained results of 82 correctly identified zeros and 5 incorrectly identified zeros, and so on. So moving on to GraphLeak, here's what the data would look like in GraphLeak. So this is the initial training data graph. And this may look super simple, but actually there are 1,000 edges all laying on top of each other between numerical nodes and true and false nodes. For each picture in the model, an edge forms between true or false, depending on whether it was correctly identified by the model. You may notice that the connections between the digit nodes and true nodes are thicker than the digit and false nodes. This is because our model has been trained to correctly identify many more digits than incorrectly, thus increasing the amount of edges between the true nodes and the digits. Then in Collab, I poisoned the set just a bit. So out of 1,000 data points, I poisoned just 10 values, where 10 of the ones are now labeled as 2. So this is not really much of an effect. Most of the numbers remain the same despite poisoning 10 data points. So that would be 1% of the total number, so it's unlikely to have a significant effect. And here I poisoned 30 rather than 10 nodes. Again, this might be a slightly bigger difference, but not really a big change. Again, the graph doesn't change all that much. It's just edges and nodes stacked on top of each other. The one tiny difference you may observe is the thickness of the edges of the nodes between 1 and true is somewhat dramatically more than between 1 and false. So now let's poison all the ones again. And in this case, all the ones become 4s now. And here are the results. So there's no 1s at all, and they're just replaced by 4. And here's what that would look like in a graph. So this actually looks pretty similar. But instead of 12 nodes, there are 11 because the 1 is missing and poisoned completely off from the rest of the nodes. And I have a comparison feature in my application, so I wanted to compare the two graphs, where one has all 1 nodes completely poisoned on the right, while on the left is the original graph with normal comparison data, and this is completely untouched. Since only 1 node was poisoned off fully, the risk rating is actually quite low. But if we poison the 2s in here into 4s, the node difference is more significant, and all the 2 nodes have been removed fully, effectively, and our risk would jump to a medium. So visualizing mathematical differences can show us how data has been tampered in a graphical format, and labeling these data points can tell us exactly how it has changed statistically speaking. What I want to illustrate is that we can also track these sorts of changes in our databases to use for threat detection. Finally, we can analyze our risk using the comparison mode feature and understand how much of our model has changed. GraphLeak was created as a graph visualization tool first, before any addition of LLMs. So my hope is to have this application as a tool for analyzing graphs, first and foremost. For future features that I would like to implement in GraphLeak, I want to do more statistical analysis. So what else can we learn from the number of nodes and edges and other statistics besides risk rating? Also, one of my favorite concepts in graph theory is cycles. So how can we implement cycles within graphs, and what do they tell us about the graph as a whole in terms of cycles and direction? And finally, I would like to integrate GraphLeak into a training model to truly show how an LLM can change over time from poisoning beyond a theoretical model. At the end of the day, context and intention are key when it comes to understanding the intended outcome of a machine learning model. This is also true and key to understanding data poisoning. For example, there's the original intention for Tay to be the friendly Twitter chatbot, and there's also the intention of the Twitter users that poisoned Tay to simply troll on the internet. This is also true for bad nets, where the original intention of the model was to recognize street signs, but this intention was poisoned by adding sticky notes into the context. This is all to say that changing data for its own sake doesn't really seem meaningful. The attacker should have a goal that they want to achieve by manipulating the data. It's also difficult and important to tell when an attacker has changed a model from its intended use case. And the goal of GraphLeak was to shed some light on this change. Ultimately, GraphLeak was the culmination of finding a way to visualize data poisoning, and by extension, data provenance, specifically by using graphs. Understanding the model supply chain and reverse engineering, so to speak, LLMs is an interesting emerging field, and my hope with this tool was to find some way to intuitively demystify and visualize some of these inner workings. GraphLeak became an example of a visual pathway to tell us whether we have correctly contextualized and working versions of a model or a poison LLM displaying incorrect or even unsafe information. Thank you.
How can I poison facial biometric data to make me appear to be someone else?
I guess you'd need access to that data set that has all of those pictures of you, right? But I think the best way to, this is beyond this talk, right? But there's a way to do this, and it's just, putting on a mask, or every time you go outside, because I assume a lot of surveillance trains on your face already, right? Cameras or whatever. And if you walk around with any sort of face covering, or even there's things that project light into the cameras and mess things up. So if they're training on your facial recognition data, then I think that's the best way to poison facial biometric data.